Hello everyone and welcome back to the class. Today in this series of circuit analysis we will study maximum power transfer. In many practical situations we design a circuit to provide maximum power to the load. Like in the case of communication system or in case of power system, the transfer of maximum power to the load is always desirable. Now we will find the conditions under which we can deliver maximum power to the load. And for this purpose, we also require the knowledge of internal losses. Because sometimes these internal losses are equal to or greater than the load, which also affects the maximum power transfer to the load. Now in finding the maximum power transfer for a linear circuit, we can use the Thevenin's theorem. The Thevenin theorem divides the given circuit into two parts. First is fixed and second is variable. Where fixed part is known as Thevenin equivalent circuit, which consists of Thevenin voltage and Thevenin resistance. Both are connected in series, where variable part represents the load. Here we can find various conditions under which maximum power is delivered to the load. And variable load is connected to the terminals A to B, and current flowing through the circuit is represented by I. Now we know the current flowing through the circuit, so power delivered to the load will be equal to I square multiplied by the load resistance. Now to find the current flowing through the circuit, we know that all the elements are in series, so voltage source divided by total resistance of the circuit, which will be equal to Thevenin voltage divided by Thevenin resistance plus load resistance whole square will give us the value of current. Now the given scenario can be applied to various cases where we have to find the conditions under which maximum power is delivered to the load. And for this, every fixed part can be replaced by Thevenin equivalent and load will remain the same. Now using the given relation, we will find out conditions under which maximum power is delivered to the load. Now for the given circuit in figure 1, the fixed part consists of a Thevenin voltage source VTh and Thevenin resistance RTh. And the variable resistor is connected to the terminals A to B. And the figure 2 represents the graph of power delivered to the load. And if analyze the graph, you will come to know that if you keep small values of load or higher value of load, the power delivered will be smaller. But if you keep the load resistance equal to Thevenin resistance, maximum power is delivered to the load. So in a practical application, if you want maximum power is to be delivered, then you must know the internal losses and can easily find a condition under which maximum power will be delivered to the load. So the theorem states that the maximum power is transferred to the load when the load resistance is equal to Thevenin resistance, as seen from the load. Now to prove the maximum power theorem, we have the relation for power delivered to the load, and we will differentiate this equation with respect to load resistance and will set the equation equal to 0. Again we will reach to the result that maximum power will be delivered when load resistance is equal to Thevenin resistance. And this will be the prime condition for maximum power transfer. Now we will find out what maximum power can be delivered to the load. For this we will use the relation for power delivered to the load and substitute the value of load resistance by Thevenin resistance. And this will give us the result that maximum power delivered to the load will be equal to Thevenin voltage square divided by 4 Thevenin. And this result is only applicable when load resistance is equal to Thevenin resistance. And when load resistance is not equal to Thevenin resistance, then we will use the earlier relation given here. Now for the circuit given in the figure 1, we have to find the value of load resistance for maximum power transfer and also the value of maximum power. Now for finding the conditions under which maximum power is transferred, we will find the Thevenin equivalent circuit for the circuit given in figure 1. Now for Thevenin equivalent, first of all we will find the value of Thevenin resistance and then we will find the value of Thevenin voltage. For Thevenin resistance, we will turn off all the independent sources present here. In the given circuit, we have one independent voltage source and one independent current source. So turning off the independent voltage source will give us a short circuit, and turning off independent current source will give us an open circuit. So the resultant circuit is shown in the figure 2. Now in this circuit, the 6 ohm resistor and 12 ohm resistor both are in parallel, which give us an equivalent of 4 ohm resistor. And this 4 ohm resistor will be in series with 3 ohm and 2 ohm resistor. So the Thevenin resistance at terminals A to B will be equal to 9 ohms. Now to find the value of Thevenin voltage, we will apply mesh analysis to the circuit given in figure 3. We will assign the mesh currents of I1 and I2. Now mesh current I2 will be equal to -2 ampere, and equation for mesh current 1 will be -12 volt plus 18 I1 minus 12 I2 equal to 0. Also, no current is flowing through 2 ohm resistor near to the load terminals, so we will use these two meshes for analysis. Now solving the equations, I1 will be equal to -2/3 amperes. Now for the value of Thevenin voltage, we will apply KVL to the outer loop, which will give us the equation of -12 plus 6I1 plus 3I2 plus 2 into 0 plus VTH equal 0. And this will result in the Thevenin voltage of 22 volts. So the Thevenin equivalent voltage of 22 volt and Thevenin equivalent resistance of 9 ohm will give us Thevenin equivalent circuit. Now the conditions under which maximum power transfer, for that the load resistance will be equal to the Thevenin resistance. So using the relation of maximum power transfer, we will have the maximum value of 13.44 watts. So the value of load resistance for maximum power transfer will be equal to 9 ohms and maximum power delivered is 13.44 watts. And thanks for watching this video.